Assalamualaikum and very good morning. My name is Rusydi Mohammed Supian. So today I'm going to present about my project for subject Advanced Communication Technology BNF 44503. So the title of this project actually is Millimeter Wave MicroStrip Path Antenna for 5G Mobile. So this here is where the technology of communication was begins. This subject was taught by Dr.Najib Mohammed Ahmed Al-Fadhali. So what is about the millimeter wave and what is relations with the microstrip patch antenna? So today, as a rapid developments of wireless system and wireless telecommunications that require a such antenna design with the improved characteristics such as antenna size, bandwidth gain and more. So this requirement allow for many design trade-off between the design, height gain, low loss, antenna size, and also high bandwidth, and 70% radiation efficiency. So microstrip path antenna have a small profile, lightweight and small size with low cost and very simple design, which make them attractive and widely used for the features suitable for flat or non-flat surface. However, profit and efficiency can be increased by using the antenna array, and proposed antenna can be array structure. Millimeter wave communication system are the great interest that require capacity of requirement for future 5G network. The millimeter wave system have the frequency of 30 to 300 gigahertz with a total bandwidth approximately 250 gigahertz that available. Although the available bandwidth of the millimeter wave frequency is promising, the propagation characteristic differ is significantly from the microwave frequency band in terms of the path loss, diffraction, and also blocking, rainfall, anticipation, atmospheric observations. So, what is the problem here we got in the millimeter wave and microstrip? So, as the development of technology evolving the antenna, more design of the microstrip path antenna for future 5G communication at the central frequency can be developed. Therefore, more complex the design, more costing the elements be made of. Moreover, to produce the antenna with a high data rate where they enable user to transmit the data from one point to other point require the complexity of the bandwidth, gain, power loss, traffic demand. So this project proposed design works on the 38 gigahertz and 54 gigahertz by having a high bandwidth, high radiation efficiency and gains. So how to solve this problem? You can see on the next, which is I am going to introduce on the CST, using the CST video to design the microwave antenna. For result and discussion, I'm going to explain on the next. So in the conclusion, a simple microstrip path antenna for the 4 element that use it in 5G. So as you can see here, it's a design of the millimeter wave microstrip path antenna, which is in the shape of the rectangular. So this is a front page. In this component of this design, that using a CSC Studio Suite to design this antenna, you can see on the component we have 3 main component, or we call it as a block, that's including for the ground plane, path, and also substrate plane. For those perimeter substrate, it require on the perimeter list that I wrote on below. So you can see here for the methodology, this a design for the microstrip antenna path. So if you can see here, the yellow one on the above is a ground, and the white is a substrate plane, and while the rectangular yellow that I can show here is a path, that also with the lines there. For result and discussion, I'm going to explain on the next. And from the design, you can see the result for this antenna, which is in the turn of the E fail. You can see here for the E fail, you can see here how was the result that I got from here. This a far field for 1.54 dB hertz dBi. You can see on the surface there, and if you can see on the 2D result that I got here, this for the PEF antenna there. How will antenna receive the signals? This is the hash field for the antenna. You can see on the screen right now. But however, if I put you can change the view of the antenna, which is you can see to the results there. You can change the view on the far field here as a 2D or Cartesians. So if you can see on Cartesian's plane for the far field, actually you can see for the far field for the far field for 1.64, 1.995 and also 2.05. And you see for the theta is directly sinusoid form here. And if you see on the screen right now, the frequency that I got from this PEF antenna is about 1.54 until 2.05 and also 1.995. And if you can see on this below, the frequency right now that I'm showing here is a 9.4 gigahertz, which is for the main loop magnitude is 4.18 dB. Main loop direction is 101.0 degree, with the angular wave is 3 dB, 110. However, for the far field on 1.995 gigahertz, the main loop is a 3.74. The main loop direction is 101 degrees, same as 1.94. And the angular wide for the 9.115 gigahertz is also same as a 1.4 gigahertz. However, for the 2.0 gigahertz, you can see on the screen right now that I'm showing, the main loop magnitude was 3.55. So basically, you can see there is a different main loop direction magnitude for each frequency that design has been created. If you want to view the far field in terms of 2D, you can see here on the screen. That's how the design was delivered. The frequencies was there. That in terms of 5D. So in the conclusion, a simple MicroStrip path antenna for the 4 element that used in 5G wireless communication was able to create a simple MicroStrip path antenna that have the 5 dual with commonly used in 5G communication was able to produce. It's a very conductive path, which is the ground plane is a dielectric called a substrate that has specific value of primitivity. The dimension of the path are smaller than the board and the floor. The dimensions of the microstrips depend on resonant frequency and dielectric constant value. That's all from me. Thank you for watching.